What happens if you stray from the right path and use exponential minus j omega t as time dependence? How does that affect the Helmholtz equation? So pause the video to scribble down some equations and pay particular attention to how you represent time derivatives in this case. Quick recap from a previous exercise where we've seen that if you use a different time dependence with a minus t, you have a time dependence cosine omega t minus phi, which is represented by a phasor e exponential j phi, and then you go back to the time dependence by multiplying it with exponential minus j omega t. Now the question is, what is the phasor that corresponds to time derivatives in this particular case? So let's take the time derivative of the left-hand side, which becomes minus e omega sine omega t minus phi. And then the question is, what is the phasor that corresponds to that? And we have a hunch that rather than multiplying by j omega, we should multiply by minus j omega. So let's see if this works. Is this equal to minus j omega? And then our original phasor, exponential j phi, exponential minus j omega t. So this is a question mark, and we need to show that this is indeed true. So continuing with our equations, so this becomes minus j omega epsilon. And then these exponentials, we can write that as a sum of sines and cosines. So let's start with the cosine. So we have the cosine of phi minus omega t. But since the cosine is an even function, we can write this as the cosine omega t minus phi. And then plus j sine. The sine of phi minus omega t, which again we would like to write with an omega t first. The sine is not an even function, so we can flip that, but the price we pay for that is also to have an extra minus sign in front here. So this becomes minus j sine omega t minus phi. Okay, and now we need to look at the real part of this expression. So we just need to look where this j and this j meet to give us a real part. J times j is minus 1. We have another 2 minus signs here, so altogether the 3 minus signs give us the final minus sign, minus omega e, and then we have sine omega t minus phi, which is indeed what we should prove here. So this is actually the same. So if we have derivations in the time domain here, in the frequency domain, that corresponds to multiplication now with minus j omega as opposed to plus j omega. That, of course, has an effect on the representation of Maxwell's curl equations in the frequency domain, because now this time we have that the curl of E is no longer equal to minus j omega mu, but to plus j omega mu h. And we also have a minus sign in the other curl equation, so minus j omega mu epsilon E. So this is what our equations look like now with this new time dependence. Good, let's proceed towards the Helmholtz equation. So just like before, we're going to take the curl of the first equation and then see what happens. So if we take the curl of the first equation, we have curl of the electric field equal to j omega mu, and just assuming here that epsilon and mu are constant, uniform media. So then we have curl of h, but the second equation tells us what curl of h is. Curl of h is actually equal to minus j omega epsilon e, which becomes omega squared mu epsilon e. So what we see here is that these two flipped signs, they come together in a product, so they cancel actually. So what we end up with is exactly the same formula as we had in the previous case. So now the calculation, of course, proceeds, but the end result will be exactly the same form for the Helmholtz equation. So nothing changes. Or to put this slightly more pedantically, the Helmholtz equation is actually invariant under a transformation where you change the time dependence from plus j omega t to minus j omega t.